Facebook was super popular like 10, 17 years ago, so it's kind of one big thing. You know, it's Facebook, like, you know, no, I'm saying that's why people don't use Facebook. Like, people don't want to use the same social media as the clients are.
All right. Hi everyone. I think we're just gonna get started. We're gonna jump right in. So in today's lecture, we're going to be talking about segmentation. So this is a pretty direct follow-up to the last lecture that we had. Yeah, so I'm just gonna hop right in. So first of all, we'll start off by talking about like what is image segmentation. You know, like I briefly mentioned like classical segmentation last time, but I'll like define what this actually means, what we're actually trying to do, and then we'll talk about how we can kind of solve it using some cool neural nets. So as some review of the last lecture, we talked about how to go from a classification model to which, you know, tells you what's in an image, to going to a classification with localization model, which tells you what's in an image and where is it in the image. And then finally we went to object detection, which was answering that same question, but for a multitude of objects within an image. So to continue that, we have segmentation. So there's two types of segmentation that we're going to be talking about. So you have semantic segmentation, which is essentially saying what type is like each section of the image. So for example, like in this thing down here, we have some image with a bunch of people. So semantic segmentation model will be like, this is person, this is background, right? Kind of separating out what each pixel corresponds to in terms of what kind of class it reads. Next, we have instance segmentation. So this is answering an even more specific question, which is not only what is every pixel on the screen, but also how are they grouped together, right? As in how is, like, if we have a bunch of people, we want to be able to separate out person one, person two, etc. So it's not just identifying what it is, but it's also identifying the different instances of whatever it is you are classifying. Yeah, so here's some examples. Like we have this image with, you know, some cows on a field, right? And it's able to, semantic segmentation, essentially able to separate out the cows from the grass in the background, right? And more examples here, right? You can separate out sky, tree, body, road, etc. So if we're looking a little bit further, right, perhaps we want to even identify these specific instances of different items, right? So we might look here, we can see in this photo, we have multiple different people. So not only is it identifying them as person, but it's identifying them as person one, person two, person three, person four, essentially creating them as separate instances of the class that we're looking at. Yeah, so I'll talk briefly about why segmentation is useful. I guess, first of all, it's a little bit more obvious maybe than some of the, even the object detection thing that we talked about. I know in last lecture, there were a lot of questions that actually led us to kind of segmentation. So hopefully it's like maybe clear why this would be useful. There's lots of applications ranging from, you know, like self-driving cars need to be able to, you know, separate out different like stop signs or objects and things, right? You need to be able to kind of separate out all those things. And talking about why segmentation is maybe difficult or more difficult than the problems that we've looked at so far. I'm going to talk about some of the like Gestalt principles. So this is basically talking about how our brains, you know, perceive different objects that we're seeing, right? So I might show you guys this image and you might recognize some sort of gradient here, right? Even though this isn't really a perfect gradient. And also it's composed of a bunch of individual objects, right? A more extreme version is you might look at this weird set of lines here and you might say, well, that's a blue circle in the middle, right? But there's no actual circle there physically, right? We're just identifying some sort of pattern within the shapes. And so this essentially, it's a difficult problem for us to, you know, write some algorithm to just detect out these shapes, right? Or detect out that that's a dog running on the right. Because things might not actually be physically connected to each other. Things might represent some sort of larger context that you want to be able to identify that isn't directly represented by just grouping together similar colors like we talked about last time. Yeah, how do we approach segmentation? So we talked last time about some classical segmentation methods that I really briefly kind of skimmed over, but we can talk about maybe how these work in a little bit more depth. So for example, let's say we have this image of some playing cards. Something that we might do is try to, essentially create connected segments by grouping together pixels based on some sort of criteria. So for example, yeah, we could look at like the intensity of 2 pixels, right? We could look at some color information. We could even, maybe run a convolutional kernel over and look at some sort of texture information, right? There's lots of different ways that we can kind of group these. We could write different algorithms to kind of group these things together. Yeah, there's like lots of examples here. So yeah, so one thing that we might decide to start off with is using CNN features. So if we have some sort of sliding window, right, that's able to slide over, right, then we can essentially get some sort of internal feature map representation and then perhaps make some decisions off of that. So as in, what we could do is we could run some convolutional filters over an image. Those would output some sort of feature map, and then maybe we could classify each element of that feature map to represent some sort of classification. So as an example, right, we have these little convolutional boxes right here, right? So this might, go through all the layers, and then in the final feature map, maybe we'll feed that into a classifier, and the classifier is going to say, this pixel is cow, right? And if we run that through the entire image, then for each pixel, we're going to get some sort of classification, and then that is our segmentation map, right, for semantic segmentation. Yeah, so this is really inefficient if we do it with sliding windows, right? Because we're going to be essentially running the CNN model over every little cropped sections of the image over and over again. This is the exact same problem that we saw yesterday. So the solution, once again, would be to use feature maps, right? Do some sort of end-to-end convolutional. So instead of running the network on a specific section of the image, like over and over again for a bunch of different sections of the image, we could actually just do this fully convolutional. So if we have some sort of input image, we'll run a bunch of convolutional filters over that image, and then we'll get some sort of output. If we design our convolutional filters in a way such that we're preserving the size of the input at the output, then we're actually able to directly have a one-to-one correspondence between an input pixel and an output pixel, right? So if we have all of these, if we have, like, for example, an input image, it's got 3 channels, right? Maybe red, green, blue, and then it's got a width and a height. If we run these convolutions over with that same kind of width and height output, then we're essentially going to get a feature map that is essentially at the exact same size, and we can simply select the class in that feature map that the network kind of outputted. And we'll get an output, for example, like this, right, where it's actually being able to segment the image. Yeah, cool. So the issue, or one issue with this, is that it's going to be really expensive. It could be really expensive to do this. And so if you're thinking about why it's expensive, right? Let's say we have like a 4K image, right? That means that every single, intermediary section of the image, right, is going to be containing, that like the 4K resolution, right? Times whatever the volume of the feature map inside for every single step along the convolutional pipeline, right? So in previous networks that we've looked at, especially convolutional networks, usually, right, let me get an eraser. Usually the ones that we've looked at so far all share a very similar structure, right? They might, they take in some input image, and then maybe they run it through, and you get some sort of hidden layer output, right? And we're getting kind of smaller and smaller, and maybe even wider, right, as we get smaller. And then maybe there's like some fully connected network at the end that produces a couple outputs, right? So the idea is here is that because this network design is kind of, squishing inwards, that we're actually able to, I guess if we were to take all of these and we were to stretch them all out to be the full size of the image, then we're essentially going to be a lot slower than doing something like this, right? Because there's a lot more weights, there's a lot more things to train, first of all, but also we're just, it's going to be a lot slower. So a potential solution to this is we want something that looks like this, but that can still output an output that is the same size as the original image, right? So we want to take an image, we want to run a bunch of convolutions on it, which make the feature map smaller, And then we want to somehow go from that smaller feature map to a full-sized image or segmentation map once again. So that process of going from like, some small image, some feature map, to maybe a larger image, is called upsampling. So the basic idea is that we can, as we're running our convolutions over the input image, it's getting smaller and smaller each time. And at the very end, we'll do some sort of upsampling to go from this little small volume at the end to a like pixel per pixel prediction for each pixel from the input image. So it's maybe a little bit unclear of how we do this at the moment, but this is like theoretically what we want to do. So I bet a lot of you have in the past, seen an image and it's like too small. So you try to go into Photoshop or something and you stretch the image out, right? And you stretch it out and the image gets bigger, but maybe it's like blurry in the middle now, right? Or because Photoshop is using some sort of upsampling algorithm. There's lots of classical kind of upsampling algorithm. A simplest one would be nearest neighbor. So if you've ever like made an image bigger and then it gets super pixelated, that probably means they're using nearest neighbor, where essentially they're just taking the color value of whatever's closest to the pixel that you're upsampling between. So in this example, if we were upsampling this little image right here with nearest neighbor, this pixel would be 10, like all of these pixels would be 10 actually, all of these pixels would be 20, all of these would be 40, and all of these would be 30. More useful ones would be like a linear or bilinear kind of interpolation, which is essentially still using those adjacent values and then somehow using some function to map in between those. But all of this is not really ideal for what we want in our situation, right? Because if we have some sort of feature map segmentation output, we don't want it to just like blur, be like, okay, if we have our feature map, right? And let's just say like for simplicity that like this is the actual image. And let's say like this corresponds to this entire section of the image, this corresponds to this entire section, right? We don't want to just simply like, interpolate directly between this value and this value for the entire section of the image, right? Because there might be some sort of texture or some sort of other information that might be able to learn to be able to upsample better. So the key idea here is that instead of using one of these just very basic like handwritten interpolation algorithms, we can actually make interpolation a learned process. So we can actually have some sort of network do this upsampling, do this entirely within some sort of learned process. So that begs the question, how do we do that, right? How do we upsample with a learned algorithm? So in order to get to that, I'm first going to do a very brief review of convolutions because it will lead us back into, or at least nicely into our upsampling algorithm, which is going to be deconvolutions. So the basic idea behind a convolution, so let's say I have some input that's like 3 by 3 by 1, and I want some output that's 2 by 2, right? Maybe we have a stride of 2 as well, with some sort of 3 by 3 filter that's going on top. So in this case, we'll take our filter, we'll place it above the image, right? It's centered around this input right here, and we'll decide that the output is going to go right here. We're going to take the filter, we're going to hold it over the image, we're going to multiply each element in the filter by those corresponding entries of the image, sum them all up, and place them in the output pixel, right? And we're going to do that, and we're going to repeat that across the entire image. So this is all hopefully stuff that you guys have seen before. But we're going to take inspiration from this and do it's not actually an inverse, but we're going to do somewhat of an inverse process to this, to kind of upsample instead of downsample. So enter deconvolution. So the basic idea behind a deconvolution is that we have some sort of small input volume and we want a large output volume. So if we kind of do a reverse of what we saw before, we'll take a target pixel in the output. So on the left, you can see that's our input, right? And we're picking a specific pixel in that input. And then what we can do is we can take like a convolutional kernel and we can place it over the output, right? So we're placing our filter over the output. Again, remember that these filters, right? Each element of the filter kind of has some sort of weight associated with it. And what we can actually do is we can take that pixel, we can multiply it by each of the weights in the filter, and we can put that multiplied value into the corresponding pixel on the output. So for example, if this had like a weight of 5 or something, and this pixel was 2, we can multiply 2 times 5 and we put 10 into this box here. And then we can continue doing this. Again, we can move the kernel along, this time along the output instead of along the input, and we can repeat this process. The key question here now is, well, we already put a value into this box, right? So do we like overwrite it? What do we do? Well, we can just sum them up, right? So we're essentially doing the similar process, but kind of in reverse of what we're doing with a convolution. So in this case, we would take, the value at this pixel, multiply it by the weight at this kernel, and then add it to the kind of existing value that was in that spot. And so the basic idea behind this, right, we can kind of extend this if our filter is maybe much bigger, right? We can kind of extend this and have it so that we can, if our stride is bigger, for example, we can even extend this to make the image, or the upsampled image in the larger. Cool. Does this concept make sense to people? Yes.
What do we do when, or I guess like there are obvious edge effects where, like, for example, the corners only get for one value. So they're going to be a smaller on average. How do we?
Yeah, great question. Fantastic question. So this is a tricky thing that is actually relevant to convolutions and deconvolutions. I think it's maybe easier to think about in the convolution sense. So if you have some convolution, right? Like let's say this is my image, right? I'm just gonna like draw a bunch of. So if you're thinking about running a convolution over this image, let's say it's like 3 by 3 for simplicity. Let's say we're looking at this pixel right here. So our 3 by 3 convolution is going over the edge, right? Oh, that was totally not what I was trying to draw. Not bad. Terrible drawing. Okay. So for looking at convolution centered on this point, it's going over the edge. So none of these pixels actually exist, right? So that would cause, if you were to just do like a normal convolution, it would kind of be ambiguous as to what you decide these values are supposed to be. A trivial solution, which I think usually maybe doesn't work very well, is you could just assume everything off the edge is 0, like it has no value. But then you get the problem of, well, this value in the output is going to be much lower than it should be, right? Because it's being summed up with a bunch of zeros, right? Another solution would be you could, for example, take the edge pixels and you could just extend them outwards. So you could say if this pixel is a 3, it's 3 all the way down, right? And that might have a better output. Another solution that some people do is they'll take the input image and they'll like flip it and place it on the outside. So like this pixel is going to be the same as this one. The next pixel is going to be the same as this one, and so on. And so that one, I think, generally has perhaps a better preservation of the actual intensities or values of those pixels on the edge cases. Does that answer your question?
I mean, in this case, we're still.
Sure, yeah. So in the deconvolution case, let's see. So the issue is less pronounced in the deconvolution case, because if you think about it, you're still. So each pixel in the input is perhaps contributing to fewer pixels in the output, but each pixel in the output still has the same number of inputs that contribute to it. As in, this pixel in the input is going to contribute to this space. This pixel is going to contribute to this space, right? They're both going to kind of be, because they're being summed up, right? You don't have the same problem that you had in the convolution case.
Or at least in this case we do, right? Because there's a plus where they overlap, but the corners just have.
Oh, I understand. My bad. Okay. Yeah. So let's see. I get what you're saying. Okay, sure. Yeah, I mean, if you want to, you could do another kind of solution. You could also do the mirroring kind of solution on the input, right? And then you'd be able to have the same number of contributions to, yeah, if you'd like to. Yeah. Cool. Okay. So.
Is there a mathematical definition for evolution?
Yes, although I'm sure there is. I don't honestly know off the top of my head. Yeah, I can come back to you on that after, because I'm sure there's some, but yeah, I believe it reduces to some sort of matrix multiplication, but I don't remember the specifics. Yeah. Cool. Okay. So yeah, so now that we have this deconvolution concept, we can use it to upsample. And in fact, we can upsample over a variety of different steps. So in this architecture that we have here, we'll start off by running a bunch of convolutions over the network to kind of downsample the original image into some sort of feature maps. Then we'll maybe hit some intermediary point, at which point we're going to perhaps start running some upsampling, right? To kind of pull together values, or sorry, not pull together values, wrong word, to sort of increase volume size as we approach getting back to the original high-res resolution, which will provide a one-to-one correspondence between input pixel and output pixel without keeping the entire pipeline the same size as the input. So this is a really powerful kind of concept because you're essentially taking an input image, you're reducing it into some smaller, maybe more abstract form, and then you're expanding it back out again to represent, a one-one kind of relationship with the original image. Cool. So a continuation of this is UNet. So before I talk about what UNet is, I'm going to explain a potential problem with the last architecture that we just looked at. So in this architecture right here, if we look at, for example, the final output, right? All the final output, like the final layer, all it's taking in input from is the previous layer, right? So it's taking input from, this sort of volume right here, and it's somehow transforming that volume into this volume right here, right? And if we look at this volume, right, these volumes were all kind of constructed using only this like really low resolution kind of middling representation, right? And so the issue is that if there are some very specific, very relevant maybe portions of the input image, like for example, if you have this image of the cows, right, like perhaps like the actual structure of the shape of like the top of the cow along the segmentation boundary, right, that information is very specific and fine, right? So it's very likely that information might not be well represented within the very low resolution kind of middle layers, right? And so when we're producing this high resolution output, we're essentially having to produce the high resolution output with no direct information from the high resolution inputs, right? Ideally, we would want our, for example, final upsample to be able to look not just at the output of its intermediary, like abstract representation of this game, but also to use some of the original information that it got from processing, like the fine-grained kind of detail of the image. So this is where UNet comes in. So UNet is essentially a continuation of what we've seen previously, but the big improvement that it adds is skip connections between resolution levels. So this is solving the exact problem that I just mentioned. If you look at the architecture for UNet, right, we have the input here, and then it goes along these layers, and there's some output over here, and you'll notice that there are these gray arrows going across. And the basic idea behind these is that if we look at, for example, one of our final output, final layers before the output, it's taking input not just from the upsampling component, but it's also taking in some feature information from a very early on process of the full resolution image, right? So this allows the network to have the improved like efficiency or decreased size from having a downsampling and then upsampling network, but it still allows the network to kind of preserve levels of detail when it's outputting the segmentation map. And these skip connections are actually present at all levels in the kind of UNet, which is why it forms this little U shape where each layer in the UNet corresponds to like a different size. So we're able to kind of transfer that information along there. Yes. Yeah, so the basic motivation behind this, okay, I'll simplify it a little bit. The most basic form of this problem that UNet is trying to solve is, let's imagine I have the following network, okay? Let's imagine I have a network where there's an input image, which is big, right? And then maybe like we have like one convolutional layer or something. And then we downsample to very small, okay? And then we upsample to really big again, and then produce some output image, right? Let's imagine this is like a super simplified version of what we see there. The issue is that this upsampling, right, from the really small abstract representation to the full-sized image, it's only able to do that upsampling using this very low resolution kind of intermediate representation, which just contains perhaps, I mean, I don't want to like personify the network too much, right? But it contains maybe this very abstract, like high level representation of what the image is of, and perhaps doesn't include details like, you know, specifics of like, oh, if there's a cow, like what is the actual texture along the edge of the cow, right? For example. And so that information, the very fine-grained detail kind of information, would be represented in this layer, right? Which is just a direct mapping from the image. So the idea is that we'll add skip connections from volumes of the same size. So as in, this is like a processing of the input image, right? We can actually feed this as an input directly into the layer that's doing the upsampling. So it can upsample using both the abstract representation as well as the fine-grained detail. Does that answer the question? Yeah. Okay, cool, yeah. And then UNet is just doing that at like a bunch of different levels as opposed to just one. Yes.
How computationally expensive is it?
I mean, relative to what, right? Like, this is definitely, I mean, if you were to look at this, right, if even if you just count number of parameters, for example, if you were to take UNet architecture and get rid of the skip connections, there's fewer parameters, right? But so it's in between this and this, right? It's somewhere in between those two, right? Because we're gaining something like some simplicity. Simplicity is the wrong word, but we're gaining something from, you know, having the downsampling. So the middle sections are a lot smaller, but we're losing something by having the skip connections because that's a lot more weights. I don't know if that answers your question. Yeah, it's I can't just like abstractly say, oh, this is fast or slow, because it's kind of all relative to the other options that we have. Cool. Does anyone else have any questions? We can. Cool. Okay. Let me get back to where we were. Okay. Yeah. So everything we've talked about so far has been talking about semantic segmentation, right? So everything that we've been talking about, it works because the output of the model is maybe, you know, for each pixel, there's a vector with like the confidence in each class, right? But that doesn't work if we want to have instance segmentation. Because in instance segmentation, you could have some sort of variable number of objects in each class, right? So you could have like 3 people or 5 people or 1 person, right? And this doesn't really fit into the model that we have so far. So if we want to expand this so taking something that we've already seen before. So let's take faster RCNN, which we talked about last time. So faster RCNN, for a brief overview of like, I'm not going to spend everything, but the basic overview of like what's important here is that faster RCNN was essentially outputting some sort of bounding boxes that it would say, this is something that you might want to take a look at, and then it would run that bounding, it would crop the image to that bounding box, and then run that through some classification. And if the classification matches, then you'd say, okay, there's an object here. That's a simplification, but that's like vaguely what it's doing, right? And you can take RCNN, you can take that architecture that I just described, and you can expand it to do instance segmentation. So the basic idea behind how this works at a very high level is that we have this image, right? We'll potentially output a potential a section of potential regions of interest to look at. Then we'll do, instead of classifying that region of interest, we'll actually run some sort of convolution over that region of interest, which will semantic segment that specific section of the image. So for example, if you have an image, and it's got 2 people in it, right? RCNN might output these 2 boxes as boxes we should consider. The segmentation, we're going to run a semantic segmentation essentially over these 2 images, which are both the first one is going to say, okay, this region is person. And the second one is going to say, okay, this region is person, right? And now we have instance segmentation, right? Because these are 2 separate identifications of, you know, the same class, but they're represented as different objects. So that's, I think, like the high level kind of idea behind what that's doing. A couple like little detail things, just for our mask RCNN in particular, right? So what is it actually doing here? It's taking those boxes, it's essentially scaling them to some fixed size. It's then running the segmentation over that little image, and then it's going to to output some sort of mask that says the image is here, or sorry, the person in this case is on these pixels, and not these ones, and then it's going to scale that back up to the size of the original image, and now we essentially have instance segmentation. Cool. Yeah, so here's some examples of something running on mask RCNN that's doing some sort of like maybe self-driving car, something where it's being able to detect cars, people, traffic lights, and it's able to separate all of those out. And you can see actually in this example, we're doing kind of both object detection and instance segmentation because also showing those bounding boxes that were used. Cool. So yeah, does anyone have any questions? Otherwise, we have a demo. Is that a question? No. Okay.
So
Yes.
Just making sure I understood.
Yeah.
Properly. So we run the instance first and then the segmentation second, working off the boxes that the instance get.
So yeah, so the basic idea is you have RCNN. RCNN is going to propose a bunch of regions, a bunch of little boxes that are regions of interest, right? Regions that you might want to take a look at. Then we can essentially run like a semantic segmentation that's looking specifically for that class. So we'll say segment this. There is a person here. Like, tell me which pixels are the person, right?
That is. Sorry.
Oh no. Yeah, go ahead.
I was gonna say, so is that one, we'll call it like machine learning program, like one, is that one, from start to end, or is there like one program for, proposing boxes and one for deciding if the boxes actually meet criteria?
Yeah, so I believe if I'm understanding your question correctly, I believe that's going to be multiple parts, as in you need one part that's going to propose the region, and then one part that's going to look at each region and do the segmentation, and then you take those outputs and then combine them together into the overall instance segmentation.
Okay, so would you generally, would you generally develop those two things together, or like, can you develop one, then develop the other, or, is it just depends?
Yeah, I mean, I would assume in the masked RCNN case, unless I'm forgetting something, I would assume that if you were to, like, for example, develop your own region proposal, you could plug that into the segmentation part of masked RCNN. Or if you were to, unless I'm misremembering something, I believe that would be the case, that you could do them separately. Yeah, for this specific architecture.
Thank you.
Of course. Cool. Yeah. So I think we'll get to the demo. So this is something that you guys might have seen or heard of already. It's called SAM, Segment Anything. It's by Meta. So this is essentially like the extreme state-of-the-art segmentation model right now. It is pretty crazy. And they have like a little demo online where I can show off to you guys kind of what it's doing. So first of all, I can just, I don't know, pick an image. What image do you want? Let's do the people. That's fun. Okay. So essentially what we can do is this SAM essentially just, ran some sort of segmentation here. And SAM is actually a little bit fancier than what we've talked about so far, because not only does it doesn't just directly output like a segmentation map, it actually allows you to kind of specify points of interest. You could say this point is part of a person or of what I want to segment, and this point is not. And then it's able to kind of, adjust the map accordingly. So let's say, for example, that I were to click on this person. So it actually identified that person's torso, I guess. So maybe it was thinking that I wanted to just identify their torso, but I could say, no, I actually want, their legs too, and it extends to just segmenting out the entire person because it's kind of recognized that was what it's looking for. I can even do something more niche, like, I don't know, let's say I reset. If I like hover over, let's say the shirt, it's going to think I'm looking for the whole shirt, but let's say I just want the number, right? I could even, remove a section from that. And you notice it's actually referencing both the 2 and the 3 because it recognized that I wanted the numbers, not just the contiguous section of the number 2. So yeah, this model is really, really powerful. I recommend you guys play around with it because it's pretty fun. And like, yeah, I don't really think there's anything that comes close to beating this at the moment. It's very, very powerful segmentation. Cool. Yeah, I think that's all I've got. I know we're a little bit early. Does anyone have any questions? Yes.
I had a question on this segmentation.
Yeah.
So, essentially, the master marks and so, like, I don't know. I understand it this way where it's like we can do like object detection first and then do semantic segmentation.
So yeah, pretty much. We're not quite doing object detection first because in the object detection case, RCNN would propose the region of interest, right? So it would propose some regions to look at, and then you'd run a classifier over those regions. And then that's like the full like object detection thing. In this case, instead of running a classifier, we're running something that does the semantic segmentation. So we're not just classifying the image, we're also segmenting it. So the kind of component that's added on, that's run on those region proposals is different than it would be in the object detection case. But it's the same first half and a different second half is maybe how you think about it. It's not doing the entire object detection and then doing the segmentation. Yeah. Does anyone else have any questions? I know I went a little fast. Sorry about that. Yes. How can you make sure it doesn't
Like,
what?
How do you like? I said, don't get how like you can map out of it.
Like yeah, so okay, so that's a bit of a tricky question to answer, because you're right that it's a very hard problem, and that's exactly why we're using a learned algorithm to do this. The basic idea that you could like I'm speaking very abstractly here, but let's say so a deconvolution is trying to solve, or the deconvolution as we're using it here is trying to solve the upsampling problem, right? So it's trying to say, like, let's say I have like maybe 4 pixels, which are given, right? These are the pixels from the original image, and we want to kind of extend this to like an image that's a little bigger, right? So it's a terrible drawing, but okay. So you can imagine that a very basic network perhaps could learn something like like a linear interpolation, right? So it might start out just doing, essentially like, okay, this is 1 and this is 4, so this will go 1, 2, 3, 4, right? That's obviously that was like the example that I gave of like the analytical or like classical kind of way of doing this. That's maybe not super helpful. In a more general sense, it's possible that let me actually go back to the architecture. So another thing to kind of consider here is that while this is much lower resolution, we might have more elements. So it might, even though the box is smaller, it's perhaps longer, right? So the feature map contains, even though it contains like fewer like pixels, I guess, it might contain more information about each pixel. So it might contain more, like each vector in the feature map contains more elements, which might contain more, like, it's kind of hard for me to explain this because I don't know how the network's actually working, right? Obviously, it's just some sort of black box, right? But the basic idea would be that it's possible that that vector might contain some sort of abstract information, like, okay, at risk of like extremely over personifying the network, right? Maybe we can say that like, oh, a vector contains information on if the pixel it's looking at is like, or if the section that this pixel represents is like a cow or something. And so then when it's doing the deconvolution and it sees like that there's a black spot here and a white spot here, then it would like draw like a squiggly line for the cow's dots, and like, this is a stupid kind of trivial example. But so it might know some information, it might know some properties from the kind of internal representation that relate to some sort of more fine-grained features, more fine-grained texture, and then it will fill in that texture essentially between the 2 points. It's really hard to like, and it's a good question. It's very hard to like answer that question because part of the reason that why we are using like deconvolutions here, some sort of learned method, as opposed to a like just writing our own little bilinear interpolation algorithm or something, is that this problem is very difficult, and it's not really clear how to upsample something generally. So we kind of just lean on the network and just say, hopefully we'll learn an upsampling method that's good enough for our use case. Yeah. Cool. Does anyone else have any questions? Okay, I think that is going to be it for today. Thanks, guys. I'll pull up the attendance form. But yeah, thanks for coming. It's not working? Oh, boy.
It will be.
It's working. It is working.
I mean, like, for me.
Okay.
Yeah, it's working for me, but not for her.
Oh, boy. Yes. Okay, try this. Should be new now. Hopefully it will work. Oh,
Function number.
Yes. Like,